Hey, so let's do this second part of our physics unit. So we're going to talk about electromagnetic radiation. So curriculum stuff you need to know: compare and contrast to each other the various constituents of the electromagnetic spectrum based on source, frequency, and wavelength. So you need to know these words. We're going to use this universal wave equation. We're going to explain that nuclear fusion in the sun produces EMR. And we're going to calculate values for any variable in the universal wave equation. Okay. So what powers the sun? Well, we just said, what powers the sun is a fusion reaction. And I got a mouse pad, so it shouldn't jump around anymore, and I can write a little bit neater. So fusion powers the sun. And what fusion is the sun is made of mostly hydrogen. So if you take hydrogen and you combine it with another hydrogen, you can turn it into helium. And that's what the sun does. So under really, really hot temperatures, hydrogen combined, they turn into helium, and that's what powers the sun. So it's fusion. So almost all of the Earth's energy comes from radiation originated in the sun, and the sun spits off two different types of radiation. So it spits off these particles, and those particles include protons, they include neutrons, and these particles called alpha particles. So these particles come at the sun, come from the sun, but luckily remember that the Earth has that magnetic field around it. And because we have that magnetic field around it, it deflects these protons, neutrons, and alpha particles, so they don't harm us. And they go to the north and south poles where not many people live. So, well, where no one lives. And the other type of radiation that the sun produces is EMR, electromagnetic radiation. And this is the light that we see. This is UV radiation, X-ray. So we'll talk about all the different types of EMR that the sun gives off. So EMR, electromagnetic radiation, is the light we see with our eyes. It's the heat that we feel with our skin. And the way that EMR is created, it's created by accelerating charged particles. So anytime you have a charged particle that's accelerating, you're going to create EMR. So when you accelerate a charged particle, this creates an electric field around that charged particle. And what we learned with electricity and magnetism is that when you have a electric field, it can induce a magnetic field, and that magnetic field can induce an electric field. And what you end up getting is you end up getting a wave that looks like this. So this is our electric field, and this is our magnetic field. And they sort of co-induce each other, and they create this light wave, and that's what light is. It's this electric and magnetic fields inducing each other. So mechanical waves, which are things like water waves, sound waves, they require a medium. And a medium is the substance that they travel through. So light waves, EMR, they travel through space. And space is basically nothingness. There's nothing in space, it's a vacuum. So there's no mediums for the wave to travel through. So that's kind of weird in terms of waves. So scientists used to have this theory where they thought that space was filled with this dense, invisible, undetectable gas called ether, and they thought that this was a medium. It was kind of like a water out in space, but we can't see it, we can't detect it, and this was a medium that these electromagnetic waves traveled through. So scientists proved that light was a transverse wave, and a transverse wave looks like this, where the particles sort of go up and down. If you look at the individual particles, they're just bobbing up and down, but the wave goes this way. So the particles go up and down, and the wave travels that way. That's a transverse wave. And transverse waves are only able to travel through solids. So this meant that if there was truly an ether in space, that this ether was a dense solid, and that didn't really make sense, right? So today we know EMR is caused by vibrating electric and magnetic fields, and electric and magnetic fields don't need a medium to travel through, and this is why it can exist in the vacuum of space. So it's almost like these electromagnetic waves create their own medium. They travel through their own electric and magnetic fields. So what it kind of reminds me of is if I had superpowers and I could create water, I could swim through anything. I could swim through the air because I'm creating that water as I move along. So that's what they're doing. They're creating their own electric and magnetic field. And as they create that electric and magnetic field, they can travel through it, and they provide their own medium. So there's some certain things with waves that you need to know about. So you need to know what a wavelength is. And a wavelength is a distance a wave travels before it starts to repeat itself. So if we measure the wave from here to here, and we took out a ruler and measured this distance, so say this was 7 centimeters, well, that would be the wavelength. And we can measure from any part. We can measure from here to here, as long as that wave is starting to repeat itself. So if we measured from here, this is called our equilibrium line that I drew in there, and it's going upwards from the equilibrium line. So if we wanted to measure one wavelength, well, now it's back at the equilibrium line, but it's going downward, so it hasn't started repeating yet. So now it's at the equilibrium line and going up, so now the wave has repeated itself. So to measure a wavelength, I would have to measure from here to here, and it would still be 7 centimeters. Oh man, my mouse pad didn't stop that from jumping. That's annoying. So if we want to determine the wavelength of this electromagnetic radiation, well, we have to count how many wavelengths are in here. So we're starting at the top and going down. So this is 1 wavelength. This is 2 wavelengths. This is 3 wavelengths. And then we have a little bit added on, right? So this little bit is 1/4 of a wavelength, right? Because if a wave, or I guess I should start at the top, like this. And this is our equilibrium line. So if this is where we're measuring from, so from here to here is 1/4, right? And then from here to here is 1/4, from here to here is 1/4, and then back to the top is 1/4. So 1/4, 2/4, 3/4, 4/4. So if we go from the top to the equilibrium, that's 1/4. So in here we have 1, 2, 3, 3.25 waves. Okay, and if we want to know how much one wave is, we just have to take our 14 meters, so that whole section is 14 meters, and divide it by our 3.25 waves, and we can find out how many meters are in between each wave. So if I go 14 divided by 3.25, then our wavelength is 4.3 meters. Okay, so that's how we determine our wavelength. So try this board question, see if you can do it. Yeah. So pause the video. So we have 1, 2, 3, 4. So we have exactly 4 waves, and this is our wavelength. So we have 115 micrometers. So 115 micrometers divided by our 1, 2, 3, 4 waves. And if we calculate that, 115 divided by 4, we have 28.75 micrometers. Oops, that was supposed to be micrometers for each wave, right? And remember that micro is times 10 to the negative 6. So we could also say 28.75 times 10 to the negative 6 meters. Okay, frequency is the number of waves that pass a point every second. And frequency is measured in the units of hertz, which is the same thing as waves per second. So it's hard to show you with a still image. So I'm going to show you with the simulation here what frequency is. Okay, so I'm going to make this oscillate. I'm going to have no end here, and we're going to have a perfect wave with no dampening. So here we have a wave, a transverse wave, that's traveling through. right? So now it's set to 1.5 hertz. So what that means is, I'm just going to pause it. So if we have, oh, can we, no. There we go. So if we talk about this point right here, and we throw a timer on there, and we time it for 1 second, so we push start, so we time it for 1 second, we're going to get, so that's 1 wave, and that's half a wave, right? So we got 1.5 waves to pass through there every second, right? I can do that one more time. So I'm just going to pause it, right? So when the wave gets high up there, that's going to be 1, and when the wave gets down here, that's half a wave. So I push play. So that's 1 wave, and that's half a wave, and you can see it hit right at 1 second there, right? So if I increase our frequency, we're just going to have more waves per second. So now we have a frequency of 3, and I'm just going to pause it, and we time it. So if we push play, oops, let's try that again. If we push play, we should get 3 waves hitting by there when that timer hits 1 second. So that's 1, 2, 3. Right when we hit a second, we got 3 waves passing by that point. So that's what frequency is. And what I want you to look at is, so now this is regular motion. So if we have our frequency at 3, I'm going to lower our frequency. So I'm going to lower our frequency to about 2. What do you notice changes? So now I'm going to lower it to 1. Right? If you notice what changed is our wavelength. So our wavelength would be from here to here. So now our wavelength is about 6 centimeters. And when I have it at 2 hertz, right, our wavelength looks to be about 3 centimeters. So when we doubled our frequency, we halved our wavelength. So that's an important relationship that we're going to talk about. Okay, so here's an example. So the following diagram shows an illustration of an electromagnetic radiation passing a detector. So it says that the time and the number of cycles here. So number of cycles is the same thing as number of waves. So we have 4 waves passing by a point in 4 times 10 to the negative 6 seconds. So what we want to get our frequencies, we want to know how many waves per second. Right? So we got to put waves up top, and we got to put our seconds down below. So if we calculate that, and we go 4 waves divided by 4 times 10 to the negative 6, we end up getting, what is that? 1, 2, 3, 4, 5, 6. So 1 times 10 to the 6 hertz. So that would be our frequency. Waves per second is the same thing as hertz. Okay, so try this one and see if you can get it, and pause the video and I will go through it. So in 1 millisecond, 740 radio waves pass an antenna. Determine the frequency. So we have 740 waves in 1 millisecond. So if you look on your data booklet, on what page is it? Let me open up our data booklet here. There we go, on the very first page. So let me show you that on the camera. So if you open up to the very first page, right, it shows that m, little m, milli here, is the same thing as times 10 to the negative 3. So instead of saying milli, we can say it's 1.00 times 10 to the negative 3 seconds. So that's how you convert that milli there. So we have 740 waves in 1 milli, or times 10 to the negative 3 seconds, and we get our frequency to be 7.4, 1, 2, 3, 4, 5, 7.4 times 10 to the 5 hertz. Okay. So all EMR is part of a larger spectrum of light, and what we see, visible light, is just a very small section of our large electromagnetic spectrum. There's way more light out there that we can't see. So different parts of the spectrum are categorized by different wavelengths and frequencies. So down here we have our long wavelengths, which are radio waves. So AM, FM radio would be in these long radio waves. Right? And these radio waves can be about a kilometer long. They're around a kilometer-ish. And then as we move up here, we get smaller. So these are microwaves. So microwaves from our microwave are about 10 centimeters long. But there's different types of microwaves other than microwaves that come from our microwaves. Wi-Fi is an example of something that's microwave frequency. So it's in that microwave frequency. Wi-Fi, 5G, LTE, all of that is in the sort of microwave frequency. And then as we get smaller, we get into the infrared. So this is heat. So when you feel heat from a flame, that's your body's able to detect that infrared frequency. You can feel the heat coming off of it, or we detect it as heat, but we still can't see it, right? Night vision cameras, so if you have like one of those Ring cameras, what they do is they have light, infrared light. So they have basically a flashlight, but that flashlight flashes infrared light. And our eyes can't detect it, so we don't see this flashlight coming off of these night vision cameras, but the camera can detect that infrared, and that's why it can see. So baby monitors work that way. Outdoor cameras with night vision would work that way. And then this little section right here, this is the only section that we can see with our eyes, and that's everything from red to blue. And then as we get smaller, we get ultraviolet. So this gives us sunburns, and then X-rays, and then gamma rays are the smallest that we have. Okay, so you don't have to memorize this order. You have this on page 3 of your data book, right? So this is the wavelengths getting smaller. So we have long radio waves, short radio waves, television, microwaves, infrared. This is what we can see. We can see from 700 to 400 nanometers, and then we have ultraviolet light, X-ray, gamma, and that's our electromagnetic spectrum. So it's all on there, and you can use that in a test, and you should use that on a test. So what all EMR has in common, no matter what it is, whether it's gamma, X-ray, radio waves, what they all have in common is they all travel at the same speed, which is the speed of light. And the speed of light is 3 times 10 to the 8 meters per second. And you have that in your data booklet as well. So because they all travel at the same speed, if we have wavelength or if we have frequency, well, we can find the other one because we all know that they travel at the speed of light. So what we can use is a universal wave equation. So this is a universal wave equation where c is the speed of light. So this is for all EMR. This is a formula that we would want to use. But if we were talking about other types of waves like sound waves, we call it v because it doesn't travel at the speed of light. It's the same formula, but it just has its own unique speed that would have to be given to you in the question. So c is the speed of light, v is the speed of any other type of wave other than EMR, f is our frequency, and this lambda, this is a Greek letter, lambda is our wavelength. Okay, so let's do an example. An excited atom in a neon sign emits electromagnetic radiation, and they give us a wavelength. Calculate the frequency. So we can use c equals lambda f, and we know the speed of light because it says that it is electromagnetic radiation, so it travels at the speed of light, and we also know the wavelength. So if we move wavelength down here, we move it diagonally that way, we can find the frequency. So the speed of light is 3 times 10 to the 8 meters per second, and our wavelength is 6.4 times 10 to the negative 7 meters. And we plug this into our calculator. So 3 times 10 to the 8 divided by 6.4 times 10 to the negative 7. And we can find out that the frequency looks to be about 4.7 4.7 times 10 to the 14. So really easy calculations there. This one is not an electromagnetic wave, it's a sound wave, and you can see they give us a speed. So a source of the wave has a frequency of 650 kilohertz, so kila. If we look that up on our data book, is the same thing as times 10 to the 3. So we want to determine the wavelength. So for this one, we want to use v equals lambda f, because it's not traveling at the speed of light, and we want to find the wavelength so we can move frequency down below. So our speed is 1250 meters per second. Our frequency is 650, but remember it's kila, so it's times 10 to the 3 hertz. And then we can find our wavelength. So if we plug this in, speed of 1250 divided by 650 times 10 to the 3, we end up getting our wavelength to be 123. So 1.9, so 1.92 times 10 to the negative 3, right? Or we can say 1.92, and if you look up what's negative 3 on your data booklet, it's milli. So you can say 1.92 millimeters as well as an answer. And the reason that I answered to 3 digits here is because this has 4 digits, this has 3 digits, so I answered to this to the least amount of digits given in the question, which is 3. Okay. So we have a board question here, and I think this is our last question. Yes. So pause the video, give it a go, and see if you can get it. An antenna of an FM radio station broadcasts electromagnetic radiation with a frequency of 104.5 megahertz. A driver in a car is receiving these FM radio waves while traveling down the highway at 90 kilometers an hour or 25 meters per second. So calculate the wavelength of this electromagnetic radiation. So this question is meant to trick you. Because we're talking about electromagnetic radiation, it's C equals lambda F. And we know this is hertz, this is a frequency, so we know our frequency and we want to find our wavelength. So we just move frequency down below. And although the car is traveling at that speed, that's not the speed of the wave. The wave travels at the speed of light. And I'm sure a lot of you tried to put in that 25 or that 90. No, if it's electromagnetic radiation, it's traveling at the speed of light. And our frequency is 104.5, and it's not just hertz, it's megahertz. So you have to look up on page 1 of your data booklet, what does mega equal? And mega equals times 10 to the 6. So it's times 10 to the 6 hertz. So when we plug all that in, 3 times 10 to the 8 divided by 104.5 mega, so times 10 to the 6 hertz, we get a wavelength of 2.87 meters. Okay, that's how you do that one. So I'll post an assignment and let me know if you have any troubles with it. Thanks for watching.